Alright, so you guys wanted to know about Kc, so I'm gonna do exactly just that. But before we learn about Kc, it's best if you revise what the equilibrium law is. Alright, so the equilibrium law states that when the reversible reaction reaches dynamic equilibrium, the product of the concentration of products raised to appropriate powers divided by the product of reactants raised to appropriate powers will be constant at constant temperature. So what does that mean? So let's assume there's this reaction 3A plus B, 3 moles of A reacts with 1 mole of B to give 2 moles of C and 1 mole of D. Alright, so if we were to put an reaction using constant, we would use Kc in this case. Kc is usually for aqueous solutions and gases. Alright, so Kc equals to this at the product, let me use another colored pen, the product of the products raised to appropriate powers. So the product of the the product of the concentration of the product. So the third bracket represents concentration, I'm sure you know that. So C raised to the appropriate power into concentration of D divided by A, concentration of A raised to appropriate powers into concentration of B. Alright, so far I assume you're with me. Alright, now let's move on to acid bases. Let me take my marker. So the basic acid base equation, as we all know, is oops, that was bad. Oh my god. I can't even get this thing straight. What the hell? Finally, somewhat. H2O plus H2O gives, damn it, hang on. Alright, let's try this one more time. It gives H3O plus, the hydronium or oxonium ion, and OH minus. Now how does it give off this? Well, we have to use the Bronsted-Lowry theory. Alright, so the Bronsted-Lowry states that acid is a proton donor while base or alkali is a proton acceptor. Now this basically works in most cases, so you have to look beyond just like hydrochloric acid and sodium hydroxide. Now if we were to look at this reaction, this H2O is giving this H2, 1 H plus is transferring over here, so that results in the formation of hydronium, while this bloke, oops, wait, I think I got it wrong, hang on, let me just alright, now much better. So this 2 moles of water react, what happens? This hydrogen, this mole of water gives away 1 hydrogen to this fellow, which is another water, which results in the formation. So this bloke becomes into hydronium, and that would make, wait a second, since this fellow donated a proton, why did I draw another line? Screw that. Donated proton, that would make this guy an acid, and this fellow here gained an electron, so that would make him a base according to the Bronsted-Lowry theory. And so we get our conjugate acid, which is the proton acceptor, so C acid, and this is the conjugate base, which is the one which loses the proton. Alright, so we got this, I hope. So now, since as you see the reversible sign in the middle, we can use the equilibrium law in this case. So let me just rub everything. Alright, so we're back to our basic equation, and alright, so since this is a reversible reaction, we can use the equilibrium law and say K equals, where's my black marker? Found it. So K equals the product of the concentration of the products raised to appropriate powers, but here both of them are 1, so we write H3O plus. So where was I? K equals to H3O plus. Damn it! Forgive my frustration. OH minus divided by H2O into concentration of H2O again, because the two products are H2O. Now, since these two are the same, we can say K equals H3O plus OH minus divided by H2O whole square. Alright, so now one thing we know, so as I was saying, one thing we know is that the dissociation of water is negligible. Let me write that down. Dissociation of water, negligible, and it's also at the same time a constant. Alright, so moving on, if it is a constant, we can say that K equals to H3O plus OH minus divided by constant. So K, wait, this has a C. So Kc into const equals to H3O plus OH minus, and constant into constant will result in another constant, which is the Ka, which is equals to H3O plus OH minus. Now, this is the dissociation constant of water. I accidentally wrote A, so let me just fix that. It's Kw. Alright, first of all, you watch this, and after we watch this, we can move on to the Ka, or the acid dissociation constant. But first, watch this one.